Namaste and welcome back to another lecture on linear algebra through geometry. In the last lecture we looked at the idea of area of parallelogram whose sides were along the directions of two linearly independent vectors, say u and v, in 3 dimension, and we figured out that the area of this parallelogram in 3D whose sides were along the two let us say vectors u and v was basically the cross product of the two vectors. I mean the magnitude of the cross product of the two vectors, that is what we saw. We left the lecture with a question that individual elements of the cross product were looking like determinants of a 2 by 2 matrix. Now what is the interpretation that we have? That is the question that we had. And the second question is, like, suppose if I have 3 linearly independent vectors in 3D, what is the geometry that is formed, and how are you going to deal with that geometry? That is the question that we left in the last class with. So we will be finding out the answer for these 2 questions in this lecture. Okay. So let us go ahead. Recall, if u and v are vectors in 3D, vectors in let us say R3 and linearly independent, then let us assume that, okay, linearly independent, then we had the area of the parallelogram with sides along u and v was given by is equal to the, so I will say the area of parallelogram was given by the length of the cross product vector u cross v. This is what we had. So the parallelogram, it basically was something like this. Say we had the coordinate axis, let us say x, y, and x1, y, x2 and x3. Assume that I had a vector which is, say this is the vector u, and I had let us say another vector which was v here. Then we said that, okay, we are going to have this to be the parallelogram formed, and we said that the area of this parallelogram was basically given by u cross v. And how did we get this u cross v? So we took this to be so the u cross v vector basically looked like this. So we also had the fact that if you consider 2 equations in 3 variables such that u1 x1 plus u2 x2 plus u3 x3 is equal to 0, and v1 x1 plus v2 x2 plus v3 x3 is equal to 0, we wanted to find out that vector which is orthogonal to both u and v, and that turned out to be the cross product of the 2 vectors u cross v, which is orthogonal to the 2 vectors u and v. That is exactly what we found out. So let us get another interpretation for the area of the parallelogram. So let us look at this. So suppose let the vector u be, let us say u1, u2 and u3, vector b is equal to v1, v2, v3. Now suppose let us look at this. Suppose we project u and v let us say onto the let us say x1 x2 plane. Now what does that mean? This is basically a vector in this is basically what you call these two vectors u and v are basically in 3-dimensional space. Now what I am going to do is I am going to project these two vectors onto the plane formed by the first two coordinate axes, namely let us call this as x1 and let us call that as let us say x2 and so on. So I am going to look at this. So I have this. So let us call this as x1, let us call this as x2 and let us call this as x3. Now what am I going to do? I have two vectors, namely u and v. Let us take this as u and let us take this to be the vector v. Now what am I going to do? I am going to project this. So I am going to look at the projection of this guy onto the xy plane, and I am going to look at the projection of this onto the xy plane, I mean x1 x2 plane, and I am going to look at the projection of u onto the x1 x2 plane, which means the third component will become 0 because you are projecting these two vectors onto the plane formed by the first two coordinate axes, or the vectors like say x1 0 0 and 0 x2 0. So it is going to be plane, and therefore the third coordinate is going to become 0, in which case the projection of the vector u and vector v onto the x1 x2 plane results in these two vectors, namely results in let us say u1 u2 0 and v1 v2 0. Now we see that these two are, we already know that we have taken u and v to be linearly independent vectors, they are in two different directions. Now this projection is also going to result in two vectors which are in the x1 x2 plane, which are linearly independent. Therefore we will have a parallelogram to be formed here, and the area of that parallelogram, so the area of the parallelogram determined by these two vectors is given by, again the cross product it works. So this is going to be given by the length of this vector, the length of this vector 0 0 u1 v2 minus u2 v1, right. This is what we are going to have, which is basically given by, since its length I am going to take this as absolute value of u1 v2 minus u2 v1. Right. Similarly, I can do this. Similarly, we can project u and v onto the x2 x3 plane, we end up getting the first component being 0. So we basically get 0 u2 u3 and 0 v2 v3. This is what we are going to get, and the area of this parallelogram. So let us call this as the area of this parallelogram, area of parallelogram so area of parallelogram, let me call that parallelogram to be, let us say pi 2 3. Let me call this previous parallelogram as pi 1 2. So area of this parallelogram pi 2 3 is basically given by this, the length of this vector. What is the length of that vector? Let us look at that is the length of, again the cross product comes into picture, is the length is basically given by the length of the cross product, and the cross product basically is this. Vector which is given by u3 v2 minus u2 v3 0 0. So, this is what we are going to have, and that length is going to be absolute value of, let us say, u3 v2 minus u2 v3, right. So, this is the area of the parallelogram in the plane pi 2 3. We are again going to look at the projection along. Let us look at this. So, we are going to look at projection of u and v in 1 3, projection of uv onto the plane, onto the x1 x3 plane. If we do this, so we are going to get x1 x3 plane. So, this is going to be u1 0 u3 and v1 0 v3, and the area of the parallelogram determined by this is given by area of the parallelogram determined by these two vectors is given by, again, the cross product, the length of the cross product, which is given by is absolute value of u3 v1 minus u1 v3. Let us call this as the parallelogram pi 1 3, right. Now, recall that the area of the parallelogram determined by u1 u2 u3 and v1 v2 v3, let me call that basically as the parallelogram pi. So, the area of pi, let me call that as pi area, is given by, what did we have? We had let us take this to be the square, which is basically given by u1 v2 minus u2 v1 whole square plus u3 v1 minus u1 v3 the whole square plus u2 v3 minus u3 v2 the whole square. So, what are we going to get? We are going to get the area square, we get pi, area squared. So, let me probably put it this way, area of the plane or area of the parallelogram, area of pi square, area of parallelogram pi whole square is basically this. So, let me write this. We are going to have area of parallelogram pi the whole square is given by, something interesting happens here, area of parallelogram pi 1 2 the whole square plus area of parallelogram pi 1 3 the whole square plus area of parallelogram pi 2 3 the whole square. This is pretty interesting because if you look at this, we just had the area square, the total area that we had, area of the parallelogram pi. Let us look at what it means. So, suppose we had this, we had our let us say we had our axis, let us say x1, x2, x3 axis we had, and assume that this was the basically the parallelogram that we were looking at. So, I am going to get this parallelogram. Now, the area of this parallelogram, what it says is basically the square of the area of this parallelogram is equal to the square of the parallelogram which is formed by the projection of these two vectors onto the x1 x2 plane, plus the square of the area of the parallelogram which is formed by projecting the two vectors onto x2 x3 plane, plus the square of the area of the parallelogram which is basically formed by projecting the two vectors u1 u2 onto the x1 x3 plane. So, this is something similar to our Pythagoras theorem, where we say that the suppose I have a vector in suppose I have this vector, let us say this is the vector let us say x. So, in 2D we have this, let us be x1 and x2. We know that the length of x square is basically given by the length of the projection of the vector x along the x1 direction, so whole square, plus length of this projection of this vector along the x2 direction, the whole square. This is basically the Pythagoras theorem. So, what we do is you project this x2 x1 direction, you take this. So, that is basically your x1 x1 vector, that length, plus you project onto this. So, it is basically the right angle triangle that gets formed. So, basically you have in a right angle triangle the hypotenuse squared is equal to the sum of adjacent square plus your opposite square. That is precisely what we see here. So, this whatever expression where we in that we had, which is here, this is basically what we say as the generalization of the Pythagoras theorem. This is the generalization of the Pythagoras theorem. So, what is the generalization? I mean, we already know that the Pythagoras theorem is basically the square of length of a vector. So, Pythagoras theorem is basically it states that the square length of a vector, squared length of a vector is equal to sum of squared length of its projections onto orthogonal axis or onto coordinate axis. And that is exactly what we see here in terms of the area. It is not a surprise, because the cross product itself is a vector, and the squared length of that vector is basically what we get as the projection of the vector onto the three different coordinate axes. In this case, because we are looking at it in terms of the area, what we do is we basically project the parallelogram that is formed by the two vectors u and v in 3D onto the three coordinate onto the three orthogonal planes that we have, x1 x2 plane, x2 x3 plane, and x1 x3 plane. So, it is basically projection onto that, and we have the area squared is equal to the sum of squares of the areas of the parallelograms that are there in the orthogonal planes. So, that is basically the that is the other interpretation of the area of the parallelogram and the cross product of the two vectors. Now, let us look at some of the properties of cross products. So, properties of cross product of two vectors of cross product of two vectors. So, what are those? Let us look at the first one. U cross U is equal to 0 for any vector U. That is something which we can easily prove. You can take this vector U to be U1, U2, U3, U2, U3, and take the other vector also to be U, which is U1, U2, U3. So, if you take the cross product, you will see that this is equal to 0, the 0 vector in fact, this is equal to the 0 vector, right, because the cross product is a vector, that is going to be the 0 vector. And you also know that I mean the cross product, in the last class we saw that the cross product was basically given by u v sin theta. So, if the two vectors are going to be the same, the angle between the two vectors is going to be 0. So, sin theta becomes 0, therefore, the cross product of a vector with itself is the 0 vector, right. Okay. The second property that we have is basically, if you take two vectors v and u, v cross u is negative of u cross v for every u comma v. So, we can this is also something easy to see. So, we will take this in another we can look at this v vector to be, let us say, v1, v2, v3, and u vector is nothing but u1, u2, u3. The cross product of v and u, the cross product of v cross u is nothing but, we have this v2 u3 minus v3 u2, and we have v1 u3 minus v3 u1, and we have v1 u2 minus u1 v2 minus v2 u1 v2 u1, and we also know that u cross v is given by v2 u3 u2 v3 u2 v3 minus u3 v2, then we have u1 v3 minus u3 v1, and we have u1 v2 minus u2 v1. If you take the negative of this vector, you basically get the other one. So, v cross u is equal to minus of u cross v. The other way to look at it is also based on the angle. We see that from u to v, you go in the counterclockwise direction, you basically get u v sin theta, and when you come from v to u, the theta angle is basically you are doing in the counterclock, you are going in the clockwise direction. So, sin of minus theta is minus sin theta, so you get negative. The third property is basically this. The third one is basically this. You scale any vector, you scale the vector of u, and then you take the cross product with this v. This is going to be t times the cross product of u and v for some scalar t. And we also have this u cross, let us say, v plus w. So, the cross product basically is given by u cross v plus u cross w, right. And the most important property of all this comes out here, fifth one. If u cross v is equal to 0, then u and v are linearly dependent. Linearly dependent, and we will say conversely if u and v are linearly dependent, then u cross v is 0, 0 vector. Yeah, u cross v is the 0 vector. Now, we have been talking about just 2 vectors. Now, what we want to do is, suppose we are given 3 vectors. Suppose we have 3 linearly independent vectors u, v and w. Three linearly independent vectors u, v and w in R3. That means you are going to look at 3 component vectors. Yeah, we are going to look at 3 component vectors u, v and w. So, what are we going to do? We are going to look at this. Say, let us take this. Three linearly independent vectors u, v and w. Let me take this to be the vector u. These are the coordinate axes, let us say x1 axis, x2 axis and x3 axis. I have this vector u and I have another vector which is say v, and I have a third vector which is say w. Now, what we see is u, v and w are in 3 different directions. They are linearly independent right now. So, what we do is, if we have 3 linearly independent vectors, what is the geometry that is going to be formed? We are going to see that it is going to be a parallelepiped which is formed. Let us look at that. So, we have this to be the vector v, and we have that to be the vector u, and we are going to get this w vector here. We are going to move it parallelly. So, this is w vector, and that is going to be my v vector. Then I am going to have this w vector here. I am going to have my w vector here, and that is going to be my u vector, and again w vector here, and that is going to be my u vector, and we see that a parallelepiped is formed. So, now the question is, what is the volume of this parallelepiped? Volume of this parallelepiped. So, that is the question that we have. So, what we will do is, in this case right now we have figured out that 3 linearly independent vectors, the geometry formed is basically a parallelepiped. Now, the question is, therefore, what is the volume of parallelepiped? We will look at the idea of volume of parallelepiped, and we will also look at the idea of 2 lines in 3 dimension, because in 2 dimension the lines were either intersecting or or parallel. That means you could either get a unique solution, or let us say infinitely many solution, or you had no solution at all because they were running parallel. Whereas in 3 dimension the idea of no solution case can be a bit different. So, we will look at all that in the next lecture. So, we will address this question, what is the volume of parallelepiped, and we will also look at the lines in 3D in the next lecture. Thank you.